Hello, everyone. Welcome to another episode of the Day Zero podcast. I'm Spectre. With me is Z. For those of you who might have missed yesterday's episode or are more focused on the binary podcasts, we are going on our summer break after 2 weeks. So May 22nd and 23rd will be our last episodes for a few months until we return in September. So just wanted to give a heads up with that. Also, we're planning to go to DEF CON this year. Still got to work at the logistics of booking the flights and stuff, but I believe we're going to make it there. Z is looking to make some Spot the Vuln shirts, so if you have any ideas or favorite Spot the Vuln challenges or anything like that, shoot them over to us on the Discord if you're interested or have some ideas there. Because, we'd like to have maybe like 2 or 3 shirts, both bounty and binary-esque type vulnerabilities. So,
Yeah,
figured it'd be a cool thing to do with the community.
I was thinking one of each. One for bounty, one for binary.
Yeah.
2 shirts is enough to wear for the conference.
I think so, yeah. And on that note, I'll let you get into the Spot the Vuln solution for this week.
Yeah, and I'll be honest, I kind of phoned home with, or phoned it in with the Spot the Vuln. This was from last week's episode. We covered the Oracle's Opera vulnerability. This
I think
code
it was
is
yesterday's
taken.
episode, actually.
Didn't I say yesterday?
Oh, you said last week's, but
it's fine. Yeah, sorry. This was yesterday's episode. We covered Oracle Opera vulnerability, which it just has to do with the order of operations here. So code, for those of you listening, I've just got a bunch of strings where it is pulling parameters out like from the request get parameter, wraps them in the sanitize parameters, big long string there because, it's Java code. It's got to be, half your screen or more for any class name or method. And the last 2 here, JNDI name and username, both are encrypted values. So what's things it wraps, it does the request get parameter, sanitizes it, and then decrypts it. Which is kind of the wrong order to do that. You'd want to decrypt the value, get what the actual value is, and then sanitize the value so it can be protected or whatever. It would exploiting that's going to depend on what the application does. In this case, they were able to exploit it. There is that bit of dependency in being able to control the encrypted value, but ultimately, just looking at this code, what should stand out is the fact that you do have sanitization of the cipher text happening rather than of the decrypted text happening.
And Rudimal in chat, just jumping back on the shirts a little bit, mentioned like the jump greater, jump above assembly one. And yeah, that's actually one of the shirts that I had originally in 2019. So.
Yeah, that was our first shirt with Spot the Vuln, was that assembly bug.
Yeah, although we didn't really give them out, we just did them for ourselves. But yeah, that was actually on a shirt. That was
a good bug for that.
But yeah, it was able to be condensed. I gotta admit, like putting assembly on a shirt in a condensed form like that's readable is like I was a little bit proud we were able to do that. It's not a super easy task, but yeah. All right, so we'll jump into our topics here. As the title suggests, we have a few TPM-based topics, our first of which is a paper from the PSP reverse researchers from the Technical University of Berlin. So this is building on some of their previous research on the PSP. I don't think we've really covered it on the podcast. I've read into it a great deal on my own, and I referenced it in the blog post that I put out on my PSP research. Basically, for those who aren't aware of what the PSP is or think I'm talking about the old handheld console, it's a platform security processor. It's embedded in every Ryzen AMD CPU. It's responsible for a lot of really important things. Key among them, you've got the root of trust, so it enforces like secure boot. It also facilitates talking to the TPM, whether that be a firmware TPM, like what we're talking about here, or a discrete TPM. It's also used for, initializing the silicon and stuff. So it has a lot of important aspects of it. So that's why it's an interesting research target. PSP Reverse has looked into it quite a bit. They've given some conference presentations. The last major piece of work they put out, I believe, was coming out with a glitch attack, which they talk about a little bit in this paper. So I'll cover that for a bit of background. So basically, the PSP will load firmware from the SPI flash, and it'll also load the public key that was used to sign or to verify that firmware. So basically, they're building on their past attack where they would do a voltage glitch on the reading of that public key and the verification of the public key. That way, they could get their own public key accepted, not just AMD's, and be able to run custom code. With that, you're then able to dump the derived secrets, including like the seeds and derived keys for secure virtualization and stuff. That was their focus of their last paper was breaking its secure virtualization or SEV. And yeah, so the TPM is what they focus on here. That's Trusted Platform Module for those who aren't aware of what it stands for. One of the major things that the TPM is responsible for is like key storage. It's also responsible for doing like measurements of the boot to ensure, the boot process has integrity. The integrity hasn't been broken. So it's pretty integral to the security of the system. So an fTPM, in particular, firmware TPM is implemented directly in the PSP, and the root keys that are used to derive like secrets and stuff are not actually readable, even if you have code execution in the PSP. They're kind of locked in these read protected slots in the crypto coprocessor. And I touched on that a little bit in my blog post as well. The fact that there's like this root key, but you can't just dump it out, even if you have, the kernel code execution on the PSP side. And that's the heart of what this paper gets into here is they actually found a bug in the CCP that allowed them to dump those root keys. So for a little bit of background on that, the CCP has its own little memory space. It's called the Local Storage Block System, or LSBs. There's like so many of them, and the slots are implemented inside of these. And you just address into this LSB space as if it were anything else. So it's like a zero-base address space. You want to access the data at LSB 0, you pass in hex 0, hex 10 for the second slot, etc. So you can reference these LSBs as like keys, which is important for doing the key derivation. For decrypting something that's been encrypted with a root key, instead of having to pass in the root key itself because you don't have it, you can just pass in the LSB identifier for where that is in the CCP's address space, and that's how the read protection works there. The problem is the CCP actually allows you to pass unaligned addresses for doing crypto operations. So where you would expect like an AES key, AES 128 or whatever, you have 16-bit key, or sorry, 128-bit key.
Well,
yeah,
16 byte, yeah.
16
bit would be very, very small.
It'd be a pretty small key, yeah.
Very weak.
Yeah, so basically like you would expect it to be on a boundary, right? Like hex first key is at hex 0, second key is at hex 10, third key is at hex 20, whatever. But the CCP allowed you to pass unaligned addresses. So you could pass hex 11, for example. And what would happen in that case is when the CCP would go to do an operation, it would bleed across the key slots. So it would use 15 bytes from hex 10, which is like a public slot, and then it would use the first byte of the next slot as the tailing byte of the key. So basically what that allowed you to do is you could brute force and kind of side channel what the read protected bytes were, by just using the crypto operation as an oracle, right? So you could do like an AES operation, what this expected ciphertext is supposed to be, and you just brute force that last byte, you figure out what it is, and then you continue on, go to hex 12, do the second one, and then you just, slowly brute force that entire key. So it's quite an interesting bug. I really like how it works. It's a really cool vulnerability. Ultimately, it comes down to the fact that the CCP allows unaligned addresses, which, it really shouldn't, but
yeah, it is. Like, it is a little bit surprising that they would use the addresses as what you provided rather than a slot identifier. You refer to as a slot identifier, which would make sense if they were to actually do that and translate it into what the actual address is. Obviously, it's a little bit better performance if you just get that from the user, but you do run into this scenario where then the user can take advantage of that. It's definitely a cool bug. I will mention, you just mentioned that it's a slow brute force, and I know what you mean. Like, you slowly brute force at 1 byte at a time, but that is faster than needing to try like all 16 bytes at a time brute force the actual key. So it is an improvement. I get what you're
Yeah, I
saying
say
there,
slow,
but
but I mean
it's
like a couple minutes. Like, yeah, it's not like slow in crypto brute forcing terms.
yeah,
So yeah, that's a bit ambiguous the way I said it. So that's a fair clarification.
yeah, like
Um,
only needing 1 byte at a time, you're doing like 255 times key size rather than to the power of key size. Or well,
yeah, it's a significant difference.
yeah,
Uh,
it becomes a difference between like can you do it and
is it
impossible in
impossible?
our time frame, in like the universe time frame or whatever.
Yeah. So yeah, by slow I meant like a couple minutes. It's not instantaneous, but by crypto standards, yeah, it's very very feasible. Um, Yeah, so and on the point that what you were talking about with like accepting addresses or indexes instead of addresses, I believe the reason for that is actually because of LSBs and like the evolution there. So LSBs used to just be storage blocks in like older versions of the CCP. They could only be used for keys. LSBs though can kind of be used for various different things. So you could use them for AES keys, you could use them for like RSA exponents. You could use it for like you know SHA HMAC as for like a key for that. You could use it for like a lot of different things. So I think the reason that they have the addresses instead of just indexing them is to have that versatility. That way you're not locked into like a particular slice.
A
You're kind of
particular
supposed,
size, yeah. Yeah,
yeah.
okay, that does make sense having the other support there. I wasn't really thinking about that.
Yeah, it's mostly just that they didn't really consider it when you are talking about these read protected key slots because they are kind of a special thing. A lot of the key slots that are used later on, are going to be initialized by the PSP itself or something. But things like the root key, um, I don't know all the specifics of how it works because it's very fascinating. But basically, I believe there's a secure fuse banks on the SoC that get mapped into these CCP slots, um, because the fuses are like encrypted on the die. So it's very interesting with how that interaction works. But because of those read protected slots and the specialty factor around them, I guess they just didn't really consider the implications of allowing unaligned addresses. So yeah, it was a bit of a silly mistake as far as like a crypto coprocessor goes, but it is kind of specific to this sort of attack. Like I could kind of see how it would be looked over. Now the cool thing is with this bug too is where it is in the CCP. I don't believe this can be patched. Like this is in the CCP ROM. Um, so go like Zen 3 and lower should be vulnerable to this attack. Basically all SoCs. I'm not sure if this was fixed in time for Zen 4. I didn't see comments on that of when this was fixed. I don't know if you might have caught that. See.
I didn't see any comments specifically about that, but they do talk about this as being like this particular attack is from pre Zen 3 CPU, so that even made it sound like this one might not that ability to read that way might not even work with Zen 3.
Fair
Because
enough.
the secret extraction, so they have kind of another step or kind of an alternative attack they can do. Um, that one works with Zen 2 and Zen 3, and then this one at the end of 4.3 on page 8, it makes mention that however, we additionally provide the means to leak the unmodified chip unique secret, which is the attack we're just talking about from pre Zen 3 CPU. So
Right. Okay.
yeah,
Fair enough. So yeah, maybe just Zen 2 and lower. Um, but yeah, and part of the reason that like the seed extraction works post Zen 2 is just it's kind of abusing the fact that you have the security processor code execution. Those are derived keys. They don't really want you to have them, but it's not as secret as the root keys and stuff. So it's just kind of like a different level of separation, I guess. But yeah, I mean, it's a really cool attack. I really enjoyed it. It's very similar actually to a bug that Flats detailed in the PS4 secure asset management unit, SAMU. I believe we just gave it a shout out on the podcast. I don't remember when that was, but he had kind of a similar bug where I think it was for HMAC operations. You could basically specify the key size. So you could just like, brute force the key that way. It's got some similarities to this issue. But yeah, while this is a really cool bug, it would require a pretty significant level of access to exploit. You would need code execution inside the platform security processor, which is not like a small ask. You would basically be doing like a physical attack, like what they did here with getting it through a glitch, or you would have to find a pretty significant vulnerability that would somehow be reachable from software, which that's a multi-step process as well. So
Yeah, I do
it's
see
probably not going to be
this.
that significant for many people, but still, it's a really awesome attack.
Yeah, I see this more as being the sort of attack that is when you physically have the hardware, right? And that is something that the TPM's kind of there. Yeah, it is part of the attack surface or the threat model against the TPM and against the security coprocessor.
For
So
sure,
like it
because a
makes
lot of
sense. Go ahead.
sorry, I was just gonna say, like, a lot of the background of wanting attestation and stuff like that is for the cloud. So it's absolutely in the threat model. I'm not trying to downplay it and say like this isn't significant. But it's not something that you're just going to be able to run on any PC out there and easily take advantage of this. It's going to be a highly targeted and tailored attack. That's going to be able to take advantage of this, and it's more for like cloud and enterprise that this matters.
Yeah, at least for now, while they're the major users of like the TPM of wanting the attestation stuff. We were just talking about passkeys yesterday.
It's kind of funny how that worked out. Because yeah, we were talking about passkeys yesterday in the TPM and how that's making the TPM maybe a bit more of a viable target against corporate entities. So yeah, this is one of those things where it right now it's I think it's more targeted towards like enterprise, but as time goes on, that might shift.
Yeah, I mean,
Continue. Go ahead.
especially with Microsoft push with Windows 11 kind of pushing for all the devices to have like TPM and all of that. Like, it does feel like it is coming more towards the consumer level. And, sure, right now, these attacks aren't necessarily going to be a concern, but in the future, as it is more adopted, as it is more used, you might see it, or at least it might be something you need to be aware of. Although, yeah, still at this point, even needing like voltage glitching, like assume you've got the physical access, the number of people that are going to be like able to pull off a voltage glitch attack is still pretty low. I mean, random
Without
person
frying the
steals your
hardware too.
yeah, random person steals your computer. They're probably not going to take it and like voltage glitch it and do this. Like it's just not part of the threat model, I think, for most people.
Yeah.
But it's still a cool attack. Like, regardless of that, I really like the attack they use here, being able to kind of abusing, like, it's almost a buffer overread attack, and abusing that with crypto.
Sort of similar aspects. Yeah.
Yeah, like it's in a sense, I mean, you do get more than that, but they're using it as just this 1 byte read each time.
Yeah.
Technically it is more than that out of bounds, but you get what I mean.
Yeah, you could do however many you want. It just makes the most sense to do it one at a time. Yeah. So continuing on TPM stuff, we also had a post out of Astral VX on a physical hardware attack to sniff the Bitlocker key across the spy bus to the TPM. This one's a little bit less exciting, less novel. Figured we give it a quick cover though, since it's quite on theme with the TPM theme. Talks a bit about Bitlocker, which is Microsoft's full volume encryption, and how Bitlocker works. Bit of a TLDR on that. Basically, you can have these encrypted volumes. The encryption key for decrypting that volume is stored in line with the data, and then the key to decrypt that encryption key is stored inside of the TPM. And I think that's called the VMK, or the
Volume master key, yeah.
volume master key. Yeah, thank you. So yeah, it goes through the process of how that works. The basis for their attack here is the fact that, so at least on older TPMs, one thing I'm not sure of is they mentioned TPM 2.0 at the start of this article. I didn't think this attack worked on TPM 2.0. So I'm not sure if I'm just missing something, but basically, when this VMK gets unsealed, it's sent across the spy bus, and it's basically just sitting there in plain text. So if you set up like a logic analyzer, tap into the spy bus lines, you can sniff all the traffic going across the spy bus, and then what they do here is they just brute force what the key is, because they don't know exactly where in the data stream the key is. So they have the ciphertext, and they try every slice of the data stream as a key. And again, it is leveraging brute forcing, but it's feasible. It's not heat death of the universe timescale. It's the matter of, like, I think they mentioned like a few hours. I'm trying to remember where they talk about the time scale. I can't seem to find it now, though. Maybe that was just something invented in my head, but I imagine it would take on the order of like minutes or hours. So yeah, they just brute force trying to get the key off the spy bus and leverage it that way. Like I said, I didn't think this attack really worked on TPM 2.0. I have seen some others do something similar. I thought in 2.0 the key was actually encrypted going across the bus, because that would make sense. You would kind of think it would work that way. But yeah, in this case at least, it wasn't, so you can just sniff that key off the bus and decrypt the data. Nothing too, you know, fascinating there. Like, there's not much you can do about it. If it's just being in plain text across the bus, you just have to like hope that somebody's not attacking you physically, which again is kind of a specific threat model. Is this isn't really going to impact very many people, but it's kind of interesting. And we do like covering some of the more physical attacks here. Like, they talk about how they got into the spy bus lines, soldered to it, and set up the logic analyzer. That is fun to talk about, and it's a nice area to look at every now and then, so wanted to give it a quick cover on the podcast.
Yeah, and that is actually one of the areas I found most interesting with this post, rather than just the fact that, okay, it's unencrypted across the spy bus, is actually just how they got access to the bus and talking a bit about that. There's a lot of background in this. Honestly, I think on most episodes we'd have just done this as a shout out. I think just because of the tie-in with our last topic, it makes sense to cover them both individually, but like it has a lot of background there. Like, it seems like a pretty solid post for kind of learning a bit about both TPM and about spy, or the spy bus. But talking about that, getting to see a little bit of it, I found that fairly interesting, or that aspect of the post to be fairly interesting, rather than the actual exploitation.
Yeah, and Rudimal mentioned in chat that's why you only boot with a password. So getting into the mitigation section, that is one of the things they mentioned. It's like enable key protectors, like an alphanumeric pin or startup key. Another suggestion is just to use the fTPM. So this is a bit of a interesting thing that I kind of glossed over when we were talking about like fTPMs and discrete TPMs and stuff. There is a bit of a trade-off there. Firmware TPM, it's implemented in software, it's on the SoC. So these types of attacks where you're trying to sniff data on the bus to try to pull keys or whatever, that's really not going to work, because you're not really going to be able to break into the on die bus to try to sniff keys going across that. Like, it's just not really going to happen. But on the other hand, a discrete TPM is considered like more secure in certain cases, and just like more versatile. So there is a bit of a trade-off when you're talking about like a firmware TPM and a discrete TPM, and it's kind of interesting bringing that up in this context. This is a bit context specific. Like, obviously the key just shouldn't be left in plain text across the bus, but that's kind of besides the point. The fact is, it is, and that's one of the things you have to deal with when your crypto coprocessor is not on the SoC, is you have to deal with those physical communication links. So yeah, it's kind of interesting. Moving away from TPM stuff, Project Zero published more of their Shannon Baseband bugs. So last time we covered them, I believe on episode 198, there was only one or two that were public. Now a good number of the other ones have gone public as well, which are fairly significant bugs, because Shannon Baseband is used in all Xenos SoCs, which is a fair amount of the Android market. So yeah, I'll let Z get into this one.
Yeah, and actually, I think when we covered this, when was 198, back in like March or whatever, I think we actually covered, looks like 4 different bugs there. So there were still quite a few, and yet there were quite a few more here that they specifically called out as seemingly a little bit more dangerous, a little bit more remotely exploitable. Like, just generally, they gave them a bit of an extension. That was actually one of the unique things, was that in their blog post mentioned giving an extension to their usual 90-day disclosure policy. I'll actually bring that up really quickly. Yeah, 4 vulnerabilities being withheld from disclosure, and I believe that is these, although we have 5 vulnerabilities for today, so one of them's kind of a mystery. Either way, it's more vulnerabilities in Shannon Baseband, and again, they're fairly trivial bugs, which is kind of the reputation that Shannon Baseband has when it comes to bugs, is they are generally fairly trivial, and this kind of keeps up with that. First one is an integer overflow when reassembling IPv4 fragments. Kind of what you would expect, just from the name if you had to take a guess. But IPv4, you can send packages either as one whole, or you can fragment them, sending fragments and just a bit at a time, and then the baseband is supposed to reassemble them, put the packet back together, and then it can be processed as necessary, whatever's going to actually handle it. The problem there is that it stores the total size, so it's getting these fragments in. It's storing the size tracked in a 16-bit variable. So if you have a size, or you send a fragmented packet that is larger than 16 bits in total size, it'll overflow, and then later it allocates a buffer based off of that tracked size value. Of course, if it integer overflow, that's going to be too small. Therefore, it's going to allocate a buffer that's too small, copies all the packets in without checking the remaining buffer size, and you get a fairly traditional heap buffer overflow there. The other issues, a moment to grab one of the links here. 3 of the other issues are actually very similar to this one. So this one I've got up here is a memory corruption when processing the accept type at SDP attribute. So attribute comes in with the accept type. You can provide multiple formats in that attribute, saying like, I think they actually have an example on here. Yeah, accept types, and they just have like A1, A2, like providing whatever random formats in there. It's going to read those formats out, and each one, it's just going to store that into a fixed size buffer. So every attribute kind of gets tossed into, I'm presuming it's like a pointer being written, so pointer to the string of whatever the attribute is. And they only allocate the buffer here for 12 of them, sorry. It's another one that's 14 types. They only allocate the buffer for 12 formats to be parsed. So read 12, when you send the 13th one, that one's going out of bounds, 14th, whatever. They're all just going to go out of bounds. And as I mentioned, this happens. So they've gone with the accept type SDP attribute. They have a very similar bug with the ACFG and PCFG attributes. Just grabbing the link here again. With that one, exactly the same bug, except it's with 14 format types and the buffers for that one. And actually, the same bug is in a third place. I might have I did open the wrong one for that, though. Sorry, I should have kind of stored the names of this a little bit better. I just have the file numbers for which one's which. Either way, they have, this is now for chat room SDP attributes. Same bug. You provide more formats, or more attributes in this case, for the chat room attribute, and it overflows. So trivial bug, really not. Given the other bugs we've seen here, I'm not terribly surprised by it. And the last bug in here is another buffer overflow and another lack of bound checking, this time with the fMTP attribute. Sorry, let me pull up the post here. There we go. We've got enough of these Project Zero ones this week. With this attribute, the main difference with this one from the other ones, it is another overflow, but this time there's an 8-byte buffer that it is parsing what it believes should be an integer that represents in this fMTP attribute. It's parsing what it believes will be the integer into this 8-byte buffer. It's supposed to be an integer, but there's no checks that the payload there is actually an integer, and it copies the entirety of the attribute into it. So if you provide it something that is longer than, an 8-byte integer, it will just go ahead and freely overflow the buffer. So straightforward bugs here. We don't get any information about exploitability and what mitigations were available there. Given that it's on the baseband, and given the reputation of Shannon Baseband, I'm going to assume these are all pretty exploitable, especially given the fact they withheld disclosure beyond the normal 90-day policy, which for Project Zero is fairly rare.
I think that's quite an indicator.
Yeah, that these are quite exploitable. And given the type of bugs, easily exploitable, but I can't actually confirm that. Just looking at it, there isn't much here that seems like it would stand in the way of exploitation. I mean, I guess you would need you would want some sort of info leak. I don't remember if we covered an info leak last time. A lot of these are just overflows.
I don't think we did. That said, I don't imagine it would be too difficult to derive an info leak with one of these bugs. It's probably fairly doable. The latter 4 bugs that you covered were pretty similar to the ones we covered on episode 198. They had the same type of issue. I think it was like emergency number lists. They had the same kind of deal where they accepted, data into these like inline slots, but they didn't validate the size of the data going into those slots or the number of slots being used. So, not too surprising seeing like variants of that. The first vulnerability with the packet fragmentation, I'm not too surprised seeing a Vuln come out of that. Packet fragmentation is just something that's pretty difficult to deal with, even in like a good code base. Like you'll find fairly mature networking stacks in operating systems that have falls due to fragmentation. It's just it's kind of a nightmare to deal with. So I'm not too surprised on that one, but it's a little bit more understandable, I guess, as a vulnerability. So I think that's probably the more interesting one of the bunch. But yeah, most of them are, it's baseband. So
yeah, I agree with you that it's the more interesting one of the bunch. I mean, it's still not that crazy interesting, but and speaking about finding bugs and fragmentation, yeah, we've covered I know we've covered a Windows kernel bug that was in IP fragmentation. I think we've covered a couple of them actually. I feel like we've probably covered one in XNU also. I don't remember for sure.
For sure.
I distinctly remember the Windows one though. Either way, yeah, it is hard, but a 16-bit size variable, that just feels like you're asking for problems. Like you're asking for the overflow at that point. Like that is, I mean, especially when you're getting something fragmented, I feel like it's almost guaranteed to overflow in a sense. Like it probably isn't, but it's really not a lot of space, and that is almost asking for it. Not to. Yeah, I'm just going to leave it with that. I understand that fragmentation can be hard to deal with, but this vulnerability is like the classic fragmentation bug in my mind.
Yeah, and to be fair, you only really see those like 8-bit and 16-bit sizes in like networking and packets and stuff, which I guess is understandable in a sense. You want to keep packets as small as possible, so
keeping the packet as small as
kind
possible.
of penny pinching a lot going down to 16-bit.
But so I mean, the size probably, I don't know, like the TCP like packet size, whatever, but I'm assuming that like the size that it actually receives in there is 16 bits. I would assume that's the case. So reading in there, I get where the developer would think, okay, we're just going to copy that same size. We've already parsed it. Let's just keep it the same. I get that reasoning and that logic. but it is kind of penny pinching. Here it's on the baseband that's processing it, not the packet itself. Because they could easily store that and store the size in just one upping the size. So if you're 16-bit, you go, if this original size is 16-bit, you'd go up to 32 bits, which gives you a lot more wiggle room in terms of handling any sort of overflow. That was kind of just a general parsing rule, actually, was like if you're reading a 16-bit value, you read into a 32-bit value. That was kind of a rule that I was taught, but that was also kind of that was not doing any sort of baseband dev. That was back with doing game dev.
Yeah, I mean, it's a fair rule of thumb, though. But yeah, I mean, like we've seen with baseband, not surprising how memeable the issues are. It's just kind of one of those areas that the code quality is not that good. And, like I said, these are somewhat high impact bugs because this is going to be shared across the entire stack of devices that run off Xenos chipsets. Which is more common in like the European and the international market. Most US phones are going to be like Qualcomm and whatever, but Xenos is fairly big in other parts of the world. I think slowly shrinking, because Xenos is Samsung's product, which is why this was submitted to Samsung. It seems like Samsung isn't even using Xenos for their newer devices anymore. So I don't know if they're just conceding the fact that it's not really that good of a chipset, not that good of an SoC, but like I said, they're still pretty popular out there, and the fact that Project Zero withheld undisclosing these bugs indicates that they're probably exploitable and fairly high impact. So yeah, and they ended up finding these through binary review. Just to give that a quick shout, because we do like to talk about the methodology when we see it. Yeah, they just found it through reversing, it seems. So
yeah, that's a little bit interesting. So I think we
yeah,
often
you would think
see
fuzzing
code
with these kinds of bugs.
Yeah, we often see code, we often see fuzzing. Don't see binary review as the methodology too often in these posts. I'm trying to think of another time when we have actually. Maybe an Apple bug.
It's been a while. Apple's
Yeah,
probably the only place I can think of immediately where you would see it with some regularity. Yeah.
Actually, you know what? I mean, what were the kernel bugs that we've covered recently, or the Windows registry bugs? I
That's a
don't
good
think we
question. I don't
even
remember if we
looked
looked
at
at it.
Yeah, now I actually want to. I'm just going to pull up.
Hopefully we can find it pretty quickly here. Because yeah, I'm curious.
If I can actually type our domain correctly, we might be able to. I'm just pulling up one here, random. Yeah, binary review.
Ah, okay.
So yeah,
cool.
I guess there have been those. We've been covering a lot of the registry stuff lately. And yeah, that makes sense. That would be binary review because we're talking about fuzzing it as being relatively difficult to fuzz. Well, I incorrectly thought, oh yeah, we could fuzz this one, but getting a crash to actually detect the bug would be a lot more difficult. So yeah, binary review makes sense there. Yeah, interesting to see nonetheless, because I think we do often see more fuzzing, more code review. Actually, mostly on the code review, so I guess binary review does make sense from. Either way, interesting tidbit there. Had to go look at it.
It's one of the lesser seen methodologies, so yeah.
Yeah, takes a lot more time and effort to go binary.
Generally, yeah. All right. So that's all the issues that we had for this week. Unless you had any last minute thoughts, C, we'll wrap it up there.
Yeah, no shoutouts this week.
All right. So thank you to everyone who tuned in. If you want to catch past episodes, you can find recent ones on Twitch and all of them on YouTube, Spotify, Apple Podcasts, and more links off of Anchor. Feel free to join the Discord and follow us on Twitter. Links for those are down below or in the chat as well. As I mentioned at the top of the show, feel free to shoot some ideas in there for the Spot the Vuln shirts if you have some thoughts on that. And with that said, we'll see you next week.